Now as you can see, we are sweeping from 0 to 300 megahertz and a cable is being connected. Now I decrease the span so that I can see less number of standing waves. Now as you can see, I am seeing a frequency, standing wave at a frequency of around 145 megahertz. Now let us say this is a maxima at around 146 megahertz, and I put a capacitive load. This is a capacitor of 220 pf. Now see, the phase has shifted. Now because the frequency is high, so the phase shift is tremendous. But if I decrease the frequency, say let us take a very low frequency around 30 megahertz. Now this being 0. Now as you can see, the phase is shifting the moment I connect a load. It has reached to a maximum. Earlier it was towards minimum. Now this is the 222 pf. Now if I connect a 33 pf as a load, now it is approaching towards maximum but not has really come to maximum. So it has changed the phase but a little as compared to 220 pf. Now I connect an inductor. Now see what happens when I connect an inductor. Now see, the phase has changed in opposite direction. So this is the effect of inductor being just opposite to a capacitive load. See it again. Now one can see the response at even high frequency. Now see, at high frequency what happens when I connect an inductor. Now this is what the phase has changed in opposite direction. Similarly, we can see the response of a capacitor at high frequency. Now see, the phase has changed much more as compared to at low frequency. Now I span it to full. Now as we have seen that this impedance bridge has got a pot inside it. So now as you can see, I am seeing a response at say 150 megahertz. Okay, and let us say we are at a maximum. Now the end being open, when I connect it to load, you can see it has not come to a minimum, whereas shorting the load end this maxima should have come to minimum, because it has got little inductance and capacitance because of the structure of this pot. Now if I connect a actual short, now this is an actual short. Now I connect an actual short. This is a perfect short rather. Now you can see it has come down to minima better as compared to this bridge. So this bridge can be used for roughly visualizing from 0 to 800 ohm what is the effect of load, but these are much better. Similarly, we can see the response of these loads when I connect say a 50 ohm load. This is a 50 ohm load. So these loads are basically high frequency loads. They go up till 1 gigahertz, so they can be used. So they are purely resistive till 1 gigahertz. Now you can see, so little mismatch is there because of the length of the cable. If we decrease the length, now you can see if this load is suppose connected right at the output, now see what happens. It is as if the length of cable has decreased. So if I connect the load right at the output, it has got same response, but the standing waves are almost none. Whereas if I connect it at the end of the cable, the standing waves are decreased. Now similarly, I connect a load of 75 ohm at the end of the cable. Now see what happens. Now the standing waves remain there because the load impedance is different than the characteristic impedance of the cable. So that's why the standing wave remains.